All right, let's talk about a subject that can feel, well, impossible: organic chemistry. But what if I told you there's a secret code? A way to turn this massive memorization task into a logical puzzle you can actually solve. Let's get into it. Does this feel familiar? Yeah. It's the classic organic chemistry nightmare, right? You're just drowning in this sea of reactions, and your brain is basically screaming, how on earth am I supposed to remember all this? But here's the thing. What if the problem isn't your memory at all? What if you've just been looking at it the wrong way? This right here, this is the game-changing idea. Forget seeing these as just static facts on a page. I want you to start thinking of every single reaction as a little movie. It's got a plot, it's got characters, and there's a clear motivation for everything that happens. Trust me, this one shift in perspective is your ticket to finally getting it. So, if every reaction is a movie, what's the plot? Well, it's surprisingly simple, and it's almost always the same story. It's all about the movement of electrons. That is the secret code we're here to unveil. Once you understand this, the rest of the subject just kind of clicks into place. This is it. This is the golden rule. The one principle to rule them all. Electrons flow from somewhere they are crowded, a high-density source, to somewhere they have space, a low-density sink. That's the secret. Seriously, almost every reaction you will ever see is just a variation of this one powerful, simple idea.
Okay, let's meet our first main character, the nucleophile. The name literally means nucleus-loving, which makes sense because it's drawn to the positive charge of a nucleus. Think of the nucleophile as the generous one in the story. It's rich in electrons, and it's actively looking to donate them. It's our electron source. And here's our other main character, the electrophile, or electron-loving. Now, this is the one that's a little needy. It's electron-poor, and it's looking to accept an electron pair to become more stable. So the whole plot of our movie? It's just the nucleophile giving its electrons to the electrophile. It's a classic chemical love story, really.
Of course, before new bonds can form, old ones have to break. And there are really two main ways this happens. You've got heterolytic fission. Think of this as the messy, dramatic breakup where one atom gets greedy and takes both electrons, creating charged ions. This is the basis for most of the reactions we care about. Then there's homolytic fission, which is more of an amicable split. Each atom takes one electron, creating these super reactive things called free radicals. Okay, so we know the plot. Electrons move from a source to a sink. But what directs the action? I mean, why do electrons move in one specific way and not another? The answer lies with the unseen directors of our movie: energy, stability, and all these subtle electronic forces happening inside the molecule. This slide shows us the energy landscape of a reaction. Think of it like a hike. The transition state is the absolute peak of the mountain. It's the highest energy, most unstable point. You can't stay there for more than a fraction of a second. A reaction intermediate, though, that's like a little valley you can rest in for a moment. It's a real chemical species, like a carbocation, but it's not the final destination. So what makes these intermediates, these little valleys, more or less stable? Well, it's our three silent directors at work. The inductive effect is kind of like a push or pull of electrons through the molecule's skeleton. Resonance is about spreading out that electronic charge to share the load. It's teamwork. And hydroconjugation is a special kind of stabilization, especially important for carbocations. These are the forces that create our electron-rich and electron-poor areas to begin with. And check this out. This chart shows what happens when those effects get to work. A tertiary carbocation, one connected to 3 other carbons, is way, way more stable. Why? Because those other carbon groups are pushing electron density toward that positive charge, helping it chill out. This stability order is one of the most important predictive tools you have. It's absolutely crucial. All right, now that we know the rules of the game, the secret code, and the silent directors, let's look at the 4 major plays in the organic chemistry playbook. You're going to see these 4 fundamental reaction types again and again and again. First up, we have substitution. This table breaks down the 2 heavyweights, SN1 and SN2. The SN1 is a patient 2-step process. First, a group leaves, a carbocation forms, then the nucleophile attacks. The SN2 is a quick, 1-step, all-at-once kind of deal. And as you can see, they have totally different preferences for speed, solvents, and the final 3D shape of the molecule. Let's zoom in on the SN1 for a sec. Step 1 is the slow step, the one that sets the pace. The leaving group just Leaves. And this only really happens if the carbocation it leaves behind is stable enough to exist on its own. That's why those stable tertiary carbons are the absolute rock stars of the SN1 reaction. Then, in step 2, the nucleophile just swoops in and attacks. Easy.
Now the SN2 reaction. This one is much more dramatic. The nucleophile attacks from the back. At the exact same moment, it kicks the leaving group out the front. This forces the whole molecule's 3D shape to flip inside out. Honestly, the analogy of an umbrella getting caught in a strong gust of wind and flipping, it is absolutely perfect.
So what about the other major plays? Well, they all follow the same core principles of stability. Addition reactions break a weak bond to add new stuff. Elimination reactions do the opposite. They kick groups out to form a nice, stable double bond. And rearrangement reactions? That's when a molecule literally shuffles its own atoms around to turn a less stable intermediate into a more stable one. See? It's always about finding the lowest energy, most stable arrangement. So, we've cracked the code. We've gone through the logic. But why does mastering this stuff actually matter? I promise you, it's not just about passing your exams. It's about understanding the fundamental building blocks of, well, everything. Now, for those of you studying for competitive exams like JEE and NEET, here is your strategy. Stop memorizing, start predicting. Look at the reaction conditions, the solvent, the other chemicals, to figure out what type of reaction it is. If you truly master the stability of intermediates, you can predict the outcome of reactions you've never even seen before. That's the key. And really, this is so much bigger than exams. These fundamental mechanisms are the foundation of modern science and technology. They're how we create everything from life-saving drugs to the advanced materials in our gadgets. Let's make it real. By understanding precisely how electrons flow in enzymes, chemists can design drugs that inhibit viruses like HIV. And by controlling those radical reactions we talked about earlier, we can create the huge array of plastics and polymers that are in our cars, our clothes, everything. This is where theory becomes a tangible reality. So, the next time you see an organic reaction, I want you to stop seeing something to memorize. See it as a puzzle waiting to be solved. See the inevitable flow of electrons. Because when you understand the rules, you're not just a student anymore. You become a molecular architect, capable of both predicting and designing chemical change. The question is no longer, what do I need to memorize? It's where will the electrons go next?